John Beverley here. I'll be talking to you today about the relationship between large language models and ontologies. So we'll start off here with large language models themselves. We'll move on to ontologies, knowledge graphs, their close kins, and that relationship I was just referencing. And then I'll describe how we might use LLMs in combination with ontologies to upgrade the semantic pipelines that we've been working on. So what is a language model? Might be a good place to start. Broadly, it's a model of the human brain's capability to produce natural language. We'll recognize it as done in speech recognition or machine translation, natural language generation, grammar induction, and so on. And roughly speaking, very roughly speaking, large language models are language models trained on massive amounts of data, just incredible amounts of data. We'll see just how much a little bit later today, but this will be our basic idea. Like, large language models are large language models. Now, this is within the scope, language models, that is, of natural language processing. And sometimes it's referred to in other disciplines as things like computational linguistics. But for our purposes, we'll talk about it in terms of NLP, natural language processing, coming at it from a computer science / engineering focus. These are groups, or this is an area that's focused on applications involving language and systems that enable interaction between computers and natural language. So NLP, and you see some of the tasking you might find in NLP goals. So that's me over, I'm the one on the left, your left, asking about Star Wars playing in San Jose, and then there's a nice little bot. We go to the same barber, clearly. Both have blue eyes. Star Wars will be playing at this place. I ask when. It is playing there. It tells me some times. Okay, blah, blah, blah. Observe all the background information that's needed here. We need like linguistic knowledge, grammar, domain knowledge, discourse knowledge, knowledge about the world, all wrapped up into this NLP goal. This stuff is, and it's driven, it's not too hard to motivate why we would need to put in the work, as much work as it would be to generate such systems. We see it all over the place in interactions with web pages and emails and texts and tweets. We have wearable technologies that use NLP, GPS, etc. There's server farms that support this stuff and software that makes it fast and scalable. There's a lot of money that's been invested in the development of NLP strategies over the years. Also, we can do things a little more sophisticated than ask about where Star Wars is playing and do more interesting, perhaps, things, some of which we'll talk about today with some of the large language models, like vibe coding. It's probably the most current fad. In any event, there are other things that language models and NLP in general can help with. Traditionally, they've been used to approach speech-to-speech translation, so just conversational spoken phrases translated and spoken aloud in second languages, so you can see here from left to right, as well as sentiment analysis. You might see this on Twitter or X, where somebody makes a post and then there's an evaluation of whether it's an excited post or elated or relaxed. You can see here on the left, high confidence of pleasantness, low confidence unpleasantness, and this is from an analysis of Kim Kardashian up you see in the top left from it looks like 101 posts of it. So sentiments about Kim Kardashian would be the assessment of this. Excited, elated, looks like it's trending in that direction. So also information extraction, you see this if you take flight. So extraction of structured information from unstructured machine readable documents, and NLP is very useful in this area. You see you might get this or get an alert if you book a flight from in your email, might populate something in your Google Calendar. Straightforward translations here and there. Also, part of this endeavor, the grammatical part that is, involves, as we've seen in previous discussion, parts of speech tagging, so the annotations of words that we're quite familiar with, at least in their grammatical structure. So who let the dogs out? Not just a question, also a slogan and perhaps an anthem if you're old enough, but also an expression that has determiners, adjectives, or not adjectives, but verbs and nouns and preposition. And then the sailor dogs, the hatch, something of a nonsense expression here, you can still tag parts of speech, whether it be grammatical or not. And of course, that is not a dape I recognize being another of these nonsensical phrases. Traditional challenges in the realm of NLP, some of which have been overcome in our current era. Words for word one-to-one mappings typically have failed, so you're not going to really get straightforward synonyms in a lot of NLP work. Order tends to matter in speech, so it's not too challenging to flip sentences around and mean things that are different between the sentences, and then choosing appropriate words for given context is not always trivial. This has just exacerbated these observations when we're encountering other languages, or indeed it's the same language with homophones, like what is a fan? It depends on the context, as well as misspellings and then semantic drifts, as you see over here in A, B, and C from the expression gay or broadcast or awful. What do we want? Natural language processing. When do we want it? When do we want what? Something appropriate here. Now, one of the traditional ways, up until recently actually, which some of these challenges have been overcome, has been the advancement of recurrent neural networks. So we've discussed neural networks, sometimes very large, embedded, complicated neural networks, and they take inputs and outputs that are treated independently. You have the inputs and outputs, you have some backpropagation algorithm helping and whatnot. However, tasks like predicting the next word in a sentence require information from previous words to make more accurate predictions. So the inputs, outputs, there need to be some kind of relationship between them, and that in traditional neural network architectures, that was just not the case. And so recurrent or neural networks were introduced to address that. By introducing feedback loops or mechanisms where the outputs from one step would be fed into the inputs of the next, allowing for that information or some of the information from previous steps to be retained. So recurrent neural networks applied this same network in a sense to each element in a sequence, and in doing so would preserve and pass on relevant information and potentially enable them to the network to learn temporal dependencies that conventional neural networks wouldn't be so sensitive to. I'll give you an analogy if that was too much jargon, but you can imagine an author writing a novel one sentence at a time, where before writing the next sentence, they reread the previous ones to maintain some kind of consistency in the story. The author doesn't start from scratch every time they write a new sentence, but instead remembers those past details, ensuring that characters and themes and plot lines stay coherent. And so the contrast here being traditional neural networks might be something more akin to just writing a new sentence, whereas this imagined author who reads the previous sentences to ensure consistency is more like the recurrent neural network structure. As you see here, so the RNN processes sequences one step at a time, keeping track of the past information with hidden states, and in doing so allows there to be some kind of reference from inputs to outputs, and in doing so, quote unquote, allows for understanding of context and continuity through those inputs and outputs. And this is much like how an author might recall past events in a story while writing the next part of the story. As you can see here, this is a typical sort of representation of how the architecture works. It's used when inputs and outputs are both in sequences of tokens. So there's some hidden states. We've seen these before, so I won't belabor it, but these hidden states are supposed to remember things up until a certain time, and then there's like an unfolding of the sequences over time as prediction is conducted. In practice, recurrent neural networks had difficulty remembering things far back. You can imagine, again, on that analogy, an author who's writing a story and rereading previous sentences. The longer they go on in the book that they're writing, the probably harder it is to remember all of the past. Similar sort of scenario here with recurrent neural networks. Computational costs, just the noise that comes with remembering previous states. It's a bit cumbersome. An idea that occurred to some people: maybe don't try to remember everything in recurrent neural networks, much like authors when writing books typically think about themes over time, not specific sentences. Attention is a mechanism that was developed to overcome this concern or this challenge with recurrent neural networks, and it helps the network focus on the most relevant parts of input sequences when making predictions. So instead of treating all words equally, or all sentences equally or whatnot, attention assigns different weights to different parts of a sequence, and this is particularly useful for long sentences or expressions with complex dependencies over time. Now we today use attention to focus on interesting parts of the input, so that nearby relevant parts can help attract focus, and irrelevant parts not so much. And so you see the sentence here: she is eating a green apple. There's high attention between eating an apple and then green an apple. And in sequence modeling problems, we can use this sort of attention focus between inputs, sometimes called encoders, and outputs, sometimes called decoders, these tokens, as well as among the inputs only. So an encoder, just to be a little clear here, it's a strategy for reading input sentences, like the cat sat on the mat, whereas a decoder is that aspect of this machine or setup that will generate the translated sentence, or a translated sentence, one token at a time. And every time there's a generated token, the decoder asks, metaphorically, of course, which words from the input sentence should I focus on right now? And so what I'm describing here is a kind of encoder-decoder attention architecture. You can see an example here when generating, for example, for instance, the word chat, when trying to translate "the cat is on the mat" into French. A decoder would give high attention weight to the input word cat, because it's clearly relevant there. Now, attention is how a decoder looks back, in a sense, at the relevant parts of input, and this is a way to avoid having to, quote unquote, look at all of the sentences in the past, which is another way here, at least, of saying compressing the entire sentence into a single vector. Analogy, just to hopefully solidify this, is attention in neural networks is like a skilled reader skimming a book that focuses only on the most relevant parts to understand the story. I'm sure you, as a skilled reader, human who has been reading for a while, at some point you get quite good at it. You don't read every sentence by sentence by sentence. You just kind of like skim through, get the relevant parts. You can probably understand a complex sentence just by doing so, especially if you become an expert in some field. You probably, if you're a college student, have encountered this over time as you're studying for an exam or reading a textbook. Instead of memorizing, hopefully you'll learn that instead of memorizing every single word, at some point you'll be able to scan the pages, quickly identify key sentences, important formulas, highlight sections that are most relevant, etc. Sometimes contemporary textbooks will actually do some of that work for you by like bolding sections, bolding definitions, like creating little breakout pages so you can focus on that. But it's essentially a way to draw your attention to what's most salient, so you don't have to remember all the details of the text. Similarly, here, attention mechanisms will allow neural networks to focus on the most important parts of an input sequence rather than all of the words, or generalizes to pixels and images, etc. equally. This is useful in, for example, machine translation and text generation tasks where the model must selectively attend to some relevant words to produce meaningful outputs. Now, that said, recurrent neural networks and this attention mechanism is still quite slow. It takes a lot of time, a lot of challenges. So these observations, these challenges led to the construction of transformers, which are deep learning models designed for processing sequences a little more efficient, quite a bit more efficiently, I should say. They have replaced recurrent neural networks by using only attention to capture relationships between words without sequential processing. There's a very famous paper in this area that kind of laid the groundwork for this strategy from the Google Brain Group, as well as some folks from the University of Toronto, or at least one folk from the University of Toronto. It's called "Attention is All You Need." Now, attention here, the self-attention is more specific. It was used when a model only needs to represent input and not necessarily generate outputs. There's this type of attention that it's self-attention where we're just trying to focus on representing the input, the encoder part, not the decoder part. And you can see this at play in like text classification or named entity recognition or just sentence embeddings or even document encodings. Here a model is not generating new text, so there's no need for a decoder, but the model lets every input token attend to every other input token. Now, self-attention allows a model to assign different attention scores to capture relationships between words rather than treat all words equally. So like the cat sat on the mat. When producing sat, the model would assign higher attention to cat since sat describes cat. And the self-attention lets cat look at mat to disambiguate the feline sense of cat rather than, the shell command sense of like concatenation or something like that. Now, when this broader transformer architecture, at least the traditional transformer architecture described in attention is all you need, their encoders just use self-attention. That's it. And then the decoder aspect use self-attention to look at its own past outputs. And then the encoder, decoder attention look at that inputs. Now, this is relevant to what we're talking about today because modern large language models drop the encoder aspect entirely and use just the decoder transformers, which is to say, only self-attention over the inputs, i.e. the prompts plus previously generated tokens. And now that should sound more familiar despite all like the kind of hand-wavy architecture talk. Now it should probably be coming a little closer to what you've encountered, the prompts plus previously generated tokens being what is attended to in the NLP processing that's going on when you're, say, interfacing with ChatGPT. It's this transformer architecture. Stories so far, then recurrent neural networks had struggled to remember earlier context, and attention solved that problem by letting the models directly look back. Through this, researchers discovered that attention was doing all the real work, and so recurrent neural networks were not needed to do similar things, and so that led to the development of encoder-decoder attention architectures and then transformers, which ultimately replaced current neural networks, even though transformers are still a form of neural networks. Large language models leverage transformer architectures to process and generate natural language text. What are these things? Well, we know, right? We play with them. We know, in a sense, they're statistical pattern recognition and prediction systems. They output the next likely token in a sequence. So token here could be something like a word or a character, and a sequence is something like a sentence or paragraph or a book. And the likelihood of the next token appearing is determined by the context in which the words are seen in a larger body of text and input to the chat. LLMs, as I said, they're language models that are large. They're trained on in an unsupervised way on open source and licensed data. The pile being one of them, the 825 gigabytes over here with web data, patents, books, archives, Stack Exchange, GitHub code, I'm sure you've read the law or seen the court cases about this, but also Common Crawl, 20 billion or 20 B. Is that a GB? 20 billion URLs, that's what it is. So GPT-3, of course, has 175 billion parameters. Recall those are kind of the assignments of weights in the network. GPT-4, 1.7 trillion parameters is the estimate. GPT-5, not exactly sure. But you can see, they're large in the sense of trained, the data sets are trained on and the information they're trained on, but also large in the sense of having a significant increase in the number of parameters over previous language models. And they're growing more than exponentially. Ah, yes. And look, and the our here is you and me, the human brain's capability to speak and comprehend language, right? Look, observe what they need to mimic a fraction of our power. You and I don't have 825 gigabytes of information in our head. Yep. I don't know if we have this many billions of parameters or trillions of parameters, but this is what's needed to even come close to our power. Responses during training were refined using question response pairs like instruct GPT from the web, from humans, or bootstrapped. That is to say, the LLM outputs would evaluate their own pairs. And then reinforcement learning with human feedback was used to reward large language models that were being trained to give appropriate responses. I'm sure you've encountered that, ChatGPT is kind of friendly, right? Sure, you've seen this, right? It's you say something, it's like, what a great response. You ask it a question, it's like, what's the weather like today? And it's like, oh my God, what a great question. It's the best question anybody's ever asked. And you're like, okay, thanks, I feel great. And it's like, oh, I'm so glad you feel great. And then next thing you know, it's buying you a drink. One thing leads to another, and you've given OpenAI $20 because you want to talk to it some more and more. But in any event, it's real chatty, it's real friendly. The thought is that during reinforcement training, the human feedback was such that it people preferred those nicer answers, and so the models just became better and better, or more inclined, that is, to answer in a polite way. I mean, it makes sense, right? You can see the contrast if it's be unlikely, I suspect, or at least it's a bit surprising if the reinforcement learning had preferred answers that were snarky or mean. What a wonderful world to imagine if somebody were to make an LLM that did that. Please do. I know I would be interested in playing with it. But in any event, there's next word prediction going on here. It's influenced by the frequency the word is seen in various contexts. And so there's also a degree of randomness, so that the word with the highest probability isn't always seen. So the next token each token as it's evaluated and output in say the text that you read from ChatGPT or one of these other LLM models, the tokens that are chosen are not the ones with the highest probability to come next based on the frequency with which the word or token has been seen in various contexts across the data set, because that would lead to a lot of very, very dry and boring responses. And so there's a degree of randomness included here, so they don't always say the most probable outputs. In some models, you can get into the back end a little bit and adjust the temperature, they sometimes call it, to make it a little, more likely to produce a token that is maybe middle in terms of probability, or indeed you could raise the temperature so that it's the highest probability, and go see exactly what I'm talking about when I say dry prose. Now, as you can see, though, the kind of upshot, without continuing on in any detail, really, large language models incorporate a wide array of training techniques and AI methodologies. They are quite impressive, but it's an ensemble approach. We've seen supervised learning, unsupervised learning, massive amounts of data, advent of transformer models with attention mechanisms, overcoming recurrent neural network challenges that were themselves struggling to deal with histories. It seems like we've overcome quite a bit of that, or at least the researchers in the space have. They are impressive. Like, there's no question. I say that in awe, really, and pleased with the results. I'm very impressed, as we should all be, and I'm very optimistic and look forward to what folks do, or researchers do with these things in the future. That said, they're impressive for some tasks, not necessarily for others. Observe, witness, the region connection calculus. So you can see here on the left, you have two little circles, X and Y. They're disconnected. That's what that DC stands for. You have next to that X, EC, Y, externally connected. This is just two circles abutting, two regions abutting. And then you have EQ here right below that, where X and Y, these overlapping and exactly overlapping regions. And then on the bottom left, you have partially overlapping. We have two regions, X and Y. They have something in common. Now, there's also tangential proper part, they say, TPP. Over here, it's the third On the top, you have the little circle x and the larger circle y. Tangential in the proper part insofar as x is a proper part of y, and tangential in that at least one side of the x circle is touching a side of the y circle. There's also x non-temporal or non-tangential proper part, I should say, and that's in the that's the fourth from on the top right. You see, that's the x circle not touching any of the y circle sides. And then you have inverses of these, both of these, that xttpy and xnttpy. So if you see third from on the bottom row, the little y circle inside the larger x circle, this is just the inverse of tpp, where you have the y part, or a side of the y circle touching a side of the x circle, and then of course you have the y in tppi y, where you have the y just floating around in the x circle without touching the y. In a discussion about large language models, John, are you going on and on about the region connection calculus? Well, let me show you. First, let me ask you to show you which of these are transitive. Which of these are transitive? What do I mean? So transitivity is a logical property of relations. Relations like disconnected or equal or partially overlapping, potentially. These are relations, not all of them are transitive. Which ones are? So transitivity works like this. For any x, for any y, for any z, if x is related to y and y is related to z, then x is related to z. That's transitivity. So I'm asking here, which of these relationships are transitive? I'll give you an easy one. X eqy is transitive. If x is equal to y and y is equal to z, then x is equal to z. I did the hard one. Now, think for a moment. Consider this. Which among these relations is transitive? If you want more time, go ahead and pause, because I'm going to click over in 3, 2, 1, and let you see. Equals is transitive, as is x non-tangential proper part of y and x non-tangential proper part inverse of y. These are transitive. Hopefully you can see why, but if not, let me show you. So just looking at x non-tangential proper part y, I have xy, and then I have x or y non-tangential proper part z, and then ask yourself if x is a non-tangential proper part of y and y is a non-tangential proper part of z, whether it is the case that x is a non-tangential proper part of z. And in fact, that is the case. As a matter of fact, I don't know how I could draw this diagram without it being true, that x is a non-tangential proper part of z. Now contrast this with a case like x tangential proper part of y. You might wonder, John, is that not transitive? Well, let's see. Start with x is a tangential proper part of y. Add y being a tangential proper part of z. And attempt, if you can, as I've done here, to create an example or a drawing where both of these are true, but it is not true that x is a tangential proper part of z. And that is what you're seeing here, because for x to be a tangential proper part of z, x, the region, will have to be touching the boundaries of the region of z, and that is not the case. So x tangential proper part of y, y tangential proper part of z, but not x tangential proper part of z. Tangential proper part is not transitive. So you and I just walked through this. Great. I'm sure you got it. Check this out. I asked, and this was, I believe, GPT-4, what RCC8 relations are transitive? It said equals is transitive, and that was it. And I said, why isn't non-tangential proper part inverse transitive? And then it gave me an answer, a bad answer. And I said, but non-tangential proper part is transitive. And it said, yes, that is true. It is transitive. And then it gave It tried to argue that it was. And then I asked, doesn't this mean that non-tangential proper part is transitive? Or inverse is transitive? And it said, you're correct. Given the transitivity of non-tangential proper part, its inverse is also transitive, and observe that it's apologizing to me throughout, which I very much appreciated because it was wrong. But then it got me thinking. So you agree that non-tangential proper part inverse is transitive now, right? Yes, absolutely. Apologize for that. My bad. Here's the bad proof. Okay, cool. Here's what I said next. But I was in fact mistaken. Non-tangential proper part inverse is not transitive. I apologize for my confusion. Here's what it said. No problem at all. It's always good to discuss things. If you have properties can be intricate and sometimes counterintuitive. Do you agree now that non-tangential proper part inverse is not transitive? Yes, I agree. Let's clarify. And then it goes on to give me a bad proof. So you're correct, it ends. The non-tangential proper part relation is not transitive. I apologize for the oversight and confusion in the previous responses. Yeah. All right, leaving us. So again, very impressive. These models are very impressive. Logic seems to be one of the areas they're less impressive on. There's some reasons to understand that, but in any event, without going into details, let's shift gears now over to ways in which we might supplement or help or be helped by them with respect to ontologies, our close kin knowledge graphs. So I'm pulling this the next set of lectures here, at least some of them, that I'll build on from this paper from Unifying Large Language Models and Knowledge Graphs, a roadmap, which I think is quite good. And the authors here lay out how you might relate large language models and knowledge graphs. So knowledge graphs, understood here, essentially ontologies that are linked up with instance data. And so I think of these things as interchangeable, barring hype. And I think it's plausible to understand knowledge graphs on the model of ontologies here. So when I'm saying knowledge graphs here, you can read ontologies and vice versa. So on the one hand, you can think of knowledge graphs as enhancing large language models by bringing domain-specific knowledge or symbolic reasoning, as you see here on the left. Some examples, things like auto-tune. It aims to align large language models with ontologies through in-context learning, enabling generation of responses guided by the ontology. This is just one example. There's also, I would classify the RAG approaches in this ballpark, at least as expanded to use graphs. So the traditional retrieval augmented generation strategies just involved retrieving documents possibly relevant to a question using keyword searches, and then asked models to generate answers based on the additional context. So the idea here would be, with traditional RAG, you would prompt an LLM and ask it for information about something, and it would use keyword search and go look through some text or pull back resources, bring answers from the text, and kind of like offload some of that processing power on the actual text that it could trust. These are effective when there's keyword overlap between retrieved documents and the questions. They're not that good at things like code or math prompts, and specifying keywords that overlaps with retrieved documentation is quite challenging. Some models would often get distracted by irrelevant content in documentation or ignore just the retrieved documents and rely on their memory anyway. Those RAG strategies have been expanded using ontologies as a way, again, to improve outputs of these models. So RAG would ground, in these cases, answers by retrieving external knowledge and with ontologies used as retrieval targets or indices, and then combine generative fluency with that curated knowledge. This has taken off quite a bit. 2023 saw a little bump in the use of RAG plus ontologies and knowledge graphs. As you see the kind of output here, RAG, of course, as the general framework, more popular by a bit of a margin, and these are counts from arXiv over 2000 or since 2020 to 2025. This is from Bart here. He gave a talk at the Ontologies and Large Language Models, the Convergence of Ontologies and Large Language Models, JOO 2025 session in Catania. Gave this talk, giving an overview of the advances in the field and the kind of growth, rather large growth, even comparatively, of RAGs plus ontologies and knowledge graphs. The idea of the simple workflow, just what essentially what I've been describing here. You have, there's Barry, great picture. He asks, what is the best top level ontology? There's some similarity searching going on. There's this is kind of dovetails from a translation into a triple. You see over here BFO is ontology. It's a type of TLO and it has the top ranking and it's labeled basic formal ontology. Dovetailing of transformation into and aggregating that into a prompt fed into the large language model that returns an answer to Barry. This is a simple workflow. You can also have a more graphical RAG base with ontology in the mix as to supplement or expand on this simple workflow. You have documents feeding into LLMs and similarity searches, both feeding into some structured tokenization going on that in turn is fed into or used to create the triple, the graph that you see here, the BFO ontology type, TLO, rank, top rank there, BFO, which again dovetails from the query offered by Barry, what is the best TLO, into that aggregate prompt that is fed into the LLM ultimately, the second LLM, there are two in play here, that then give him the output, which presumably will be BFO. Now over in the middle section, we see a relationship here where large language models generate knowledge or provide general knowledge or processing to inform or augment knowledge graphs or ontologies. So here a case study, a comparative analysis of GPT-4 for automated mapping. And as you'll note, this study here evaluated 4 distinct GPT-based approaches for mapping local medical terminologies into SNOMED. So here we have like the use of GPT as a way to construct mappings for terminologies into SNOMED. And so SNOMED, of course, being a standard here using knowledge representation in the medical community. We're trying to like expand or broaden the scope of knowledge stored in here and using GPTs to do that. I too have used GPTs to expand through at least translations and from syntaxes into syntaxes that allow me to create different logical perspectives on the same domain. So I've done this using, say, GPT-5 to go from one automated theorem proving syntax to another, because not all the automated theorem provers out there use the same language. I sometimes want to check out how different automated theorem provers perform, and sometimes this gives me different results based on the algorithms underwriting these theorem provers, and that can give me new insights into the domain. Ultimately, even though I'm working in kind of a broader, more sophisticated logical language, these can give me further insights into how to represent this information for a given domain in OWL, which will inform how I build my knowledge graphs. Now that's a few more steps removed from using GPT just to generate mappings or based approaches for generating mappings into local terminologies. But we don't have to stick directly with just using brute force text. We can also, as we'll see in a moment, and I'll talk a bit more about in my own practice, use GPTs as something of a glue, all to the same end, which is, as I was saying, in increasing or improving or promoting or advancing the state of knowledge representation ontologies using these very interesting architectures. There's also this feedback loop strategy that was identified in this paper, is just synergizing LLMs and knowledge graphs, like generating facts that in turn generate knowledge. Here's a case study that was discussing this, also using SNOMED and LLMs. Here you have a range of things being discussed or evaluated. The main approaches for integrating SNOMED in this case were incorporating it into LLM inputs, using concept description to expand the training corpora of the data, and also integrating SNOMED into additional fusion modules, as well as using it as an external knowledge retriever during inference. A lot of the tasking, according to this scoping review, was medical concept normalization followed by entity extraction or type classification. So usually there's like a suite of different, really like a buffet of different things going on in the scoping review and the use of SNOMED CT. Some of them are going to fall a little closer to that, that first bucket where we're using the LLM to improve the ontologies. Some are going to fall into that use of the LLM or the ontologies to improve the LLM's outputs, and then some of them are just going to be more or less on that feedback loop, improving knowledge, improving inputs and outputs, improving knowledge in a cycle. Now, LLMs are attractive. These examples here were from the medical ontologies. We can generalize this. They're certainly attractive as natural language interfaces and they do simplify interactions, but workflows in general are complicated. There are lots of tools and formalisms and semantics and paradigms that already exist, whether it's medical ontologies or otherwise. There's a concern that over-reliance on LLMs can lead to issues that are subtle, like ambiguities and shortcuts, hallucinations, high-quality data loss. These are like the standard warnings. Hopefully I'm not saying anything that is novel or crazy. You shouldn't just bluntly rely on them. You should be careful about their outputs. Also, you should observe that we have a bunch of tools already that we know work. And often what gets in our way, whether we're dealing with like the biomedical space or cybersecurity or like, like modeling, supply chains or whatnot, is not so much that we haven't developed good tools to evaluate aspects of the domain or like get good results. It's often that we can't stitch these things together very effectively. They're often siloed. So my suggestion, whether it be in bioinformatics, healthcare, wherever these technologies are being used, instead of replacing existing specialized tools, with LLMs, we leverage LLMs as something like middleware between them. The question then arises, which languages and which tools should we be using for various purposes with LLMs as middleware? This incidentally, I think, cuts across that unified approach, so I don't find it fitting in with any of those three. I feel it's something like cutting across them. It's more or less using LLMs as a way to like connect together specialized tooling, whether it be for knowledge graphs or ontologies, whether it be for, but always, I guess, in the interest of creating better outputs and more trustworthy outputs. So a high-level example of what I'm getting at here is an NLP interface that feeds into LLM translation into formal languages. So you have like a natural language representation. There's a translator that feeds into something like a draft ontology, or does some constraint validation, or simulates processes or formulates rules. The translator, you can see being here, is like middleware for modeling tasks, where you have at the top like draft ontology in OWL, constraint verification done in like Shackle or an Alloy Logic or some automated model checker. You can also have it translate into like Simulink or Wolfram system modeler, some simulation technologies, or constraint logic architectures. So basically using the translator here, or from NLP, from natural language, or perhaps another syntax, from one syntax to another, as I was describing a moment ago, using the LLM as a way to glue or connect the tool up to what you're saying or what's being said in other documentation. Then can iterate and refine on the models, taking the output of, say, OWL, having it vetted and evaluated, taking the output of Alloy Logic, having it vetted, etc. So here's some example of modeling tasks of language tools with native out-of-the-box support. This is from a paper. You'll see some familiar faces over there. It will be presented at the beginning of December at the Winter Simulation Conference, from over-reliance to smart integration using large language models as translators. between specialized modeling and simulation tools. And you see some of the modeling tasks I had in mind when putting this together were like things like merging models. You might want to connect different models or ontologies, and there's some existing tools you can use to do so. They're a little tricky sometimes to get to work together. Some of them are reasonably good, and so you can use the LLMs to help you merge or help you bring these ontologies together. In fact, this is something that we ultimately will be trying to do in our work here. You can also think about building a model from a corpus, like doing some text analysis on data. There's some technologies out there that might be benefited from using an LLM as middleware, as well as validating model structure. So you have first-order logic languages like an OWL or Alloy, UML even. They're tools like a Hermit Reasoner. You might use Vampire or something. Some of these automated theorem proofs. I'm a fan of TLA Plus if you're thinking about validating structure that is more or less simulate or could be simulated in a finite state machine. In any event, you can use, again, LLMs here as a middleware between the way you're speaking or representing a domain and the analyzer itself or Hermit itself. Also, and just as importantly, you can use it as middleware as doing some translation between representations in the OWL and representations in a language like that of the sort that TLA Plus would use or that Alloy would use, because those syntaxes are not always the same, and it is a pain translating between them. You can also use LLMs to explain or document models. So given structured model descriptions, I mean, if you have a set of axioms, an OWL or otherwise, that you're interested in, you don't want to write all the documentation out to describe the logic. You can use LLMs as a way to kind of get the point across. You should, of course, pay very close attention to the output, because as you've just seen, they don't be too nice, because they'll be too nice back and say something wrong. So I direct your attention to this paper if you're more interested in some of the details, but I'll give you some more LLM mediated modeling workflows that might be of interest, and then try to connect up tools and roles and integration patterns that perhaps are get some juices flowing when you're thinking about using LLMs as middleware. So you might be interested in drafting an initial model structure from natural language. Use GPT-4, right? Like use Protege 2. I mean, the LLM role here would be in translating textual input to structured representations. And you can just tell it what to write. Tell it exactly what to write in Turtle, right? Output should be a target tool compatible syntax like RDF-XML, and you can test that. They're validators. You can pass it on to validators. Like you can just use RDF-lib to check it, right? Check the output and make sure that it's valid. You might also want to just do some ontology model or alignment. You can use some recommended tools here, Gonto Aligner, and then here this would be a way of suggesting initial mappings between terms and perhaps explaining inconsistencies. There's specialized tools in this case to perform alignment and consistency checking, while the LLM might mediate error resolution. So it can help you uncover or unearth some of the incompatibilities and try to sort them out. I'll skip through here. I don't want to read all of these, but I'll drop down to model verification and logic enforcement. That's the fourth row here. You might leverage tools here like Alloy Analyzer or Hermit Reasoner, or even Shackle Validators. LLM role in this case would be to convert informal constraints to formal rules, translations across syntaxes, explaining violations, and then ultimately providing human readable feedback on validation results. At the bottom here, you see in the bottom row, workflow orchestration. So here, a recommended tooling might be GPT-4 plus LangChain and an API to dispatch subtasks to appropriate tools to help you manage the workflow, right? These things can be a bit thorny. This will require some modular design and tools exposed to APIs, but it certainly can save you a lot of trouble rather than trying to do all of that orchestration yourself, especially if you have a complicated workflow like the sort we no doubt encounter regularly. So going forward, what's the point? So automate, we're always trying to automate as much of the ontology engineering workflow as possible, because it takes too long to do what we do and it involves too much manual labor. We can leverage LLMs as middleware to ease the development burden. And then existing specialized tools already battle tested rather than brute force prompting plus hope. So ultimately, then mapping the task in the context of medical ontology applications or combination of specialized tools as well as others. So I gave you several examples just from the biomedical community. There seems to be a lot of work going on in that area, in that space around using middleware or LLMs as middleware here, not restricted to the medical ontology context, of course. More general, other groups are doing it too. We will expand and use this as middleware. Hopefully you will, that is, as well. So moving on then to upgrading semantic pipelines. So clearly LLMs have limitations. They hallucinate, no structural guarantees, no notion of identity, poor multi-step stuff. They stole your lunch, they punched you in the face. Ontologies, reasoners, shackle, QC queries, and continuous integration can help give us some reliability in our workflow and development. Now, we've been building semantic pipelines. Pretty proud of them. I'm pretty proud of you for them. We so far pretty good at ETLing a little bit, like some basic ETLing. You can take in some sensor data, some text, some definitions. Hoping we'll be using LLMs going forward as middleware. Maybe you've already been doing this. Maybe we'll be doing it a little more going forward as we close out the class. But we've also come in contact with several tools that we might use LLMs as middleware to connect up. So Mal for deep learning, RDF-lib, Robot, Elk and Hermit for reasoning, and Sparkle for quality controls, and then Shackle for validation. And of course we have an automation layer here, GitHub Actions. Got you guys running pipelines on data for ontologies changes and stuff that's basically repeatable and auditable, as you see in the workflow tests that I've been writing that you've been passing. So what do we have? Like a lot of this stuff we've covered, a lot of this stuff we've come in contact with, some of the stuff we have not. So in your pipelines, I gave you a design pattern, right? One design pattern for CCO. We should expand that. We did discuss mappings from like BFO and IES, or potential mappings between BFO and IES, and CCO, and either the time ontology or QUDT. But we didn't really develop mappings. We kind of had some scripts that suggested mappings. And we certainly haven't used LLMs as middleware to propose mappings or suggest Sparkle queries or produce Shackle, or maybe you have, but I hadn't. So these are areas we're going to explore coming up. Just to give you an overview, like I guess one last shot though at how you might use LLMs to improve that semantic pipeline. Even with the stuff that we've already covered, you can have it to help with ETL. So the pattern detection and messy schemas, you get a bunch of bad data, it's got a bunch of stuff missing, or at least you use it to identify what's common in what should be common in the common data model, the canonical model that you use to line everything up. You want to normalize labels and units and temporal expressions, you can use LLMs for that. You can also suggest canonical terms for new design patterns. Like you can really use it to use LLMs to offset some of that traditional manual labor in sorting out that what should be canonical from your during your ETL. You can also use it for mapping assistance, so it could generate candidate mappings just off the cuff, for like the measurement ontology in a QEDT or W3C time from CCO time, and then perhaps even extract rationales from definitions for why these mappings are plausible. And you can compare their terminological similarity, and then evaluate mapping plausibility before reasoners are used to check consistency. You might also use LLMs to enrich ontologies. So rewriting definitions, i.e. from IES into the X's and A that Z's form, would generate candidate axioms for them. Rate axiom plausibility, maybe with hybrid scoring with MAL, as we had in Project 5, wink wink, or suggest constraints for Sparkle QC or Shackle validation. Indeed, you can also go over to pipeline automation with LLMs and have it support through generating or modifying workflow scripts or producing textual summaries for validation reports. We haven't had many validation reports. I mean, some in the terminal, but maybe you want more. And you can also include more information for debugging strategies when pipelines fail. I left you guys out in the desert, kind of sparse. Maybe you want more. Maybe you can get more. Your final project here will help you kind of tie some of this together. It'll help you, hopefully it will help you tie together the various toolings and strategies we've been uncovering, as well into your newfound knowledge of large language models and their transformer architectures, and as well as their use as middleware between existing tools that you have learned to use in this class. I want you to enhance your semantic pipeline, either by extending the ontology mapping capability that we uncovered in Project 3, or by expanding the ingestion of new data and new design patterns in the semantic pipeline project for project proper. So for option 1, we got data plus design patterns expansion. So here you'll be demonstrating how to extend your existing semantic pipeline to a new domain or new type of data. So if you recall, I fed you the data for that project, for project 4. I fed you the data with your semantic pipeline, and I also gave you a design pattern for information in CCO. Here, large language models may help with detecting new schemas and normalizing them, suggesting a new design pattern or 2, aligning new domain patterns to existing patterns, auto-generating the Sparkle, QC, and Shackle, or proposing new axioms that govern the new data domain. Just some examples. And here you might leverage existing symbolic tools to confirm, like you can check for unit consistency with robot and elk. You can also check for shape constraints satisfied using Shackle and the validation tools such as Shackle Playground with an API you might call. All new axioms can be checked for consistency, obviously OWL. QC queries should be returning 0 results. There's a Sparkle Playground too. You can set up a local Sparkle environment to check, incidentally. Set up a little server if you want to, or just use it in the terminal. I mean, that's what I was doing. You can also check that the pipeline runs automatically with GitHub Actions and make it easier or flow better using LLMs as some guide. Now for the other option for a project, it's your final project, demonstrating how to automate the generation of and evaluation of mappings between ontologies. So this was that project 3. This is a continuation of that. LLMs here might help with suggesting candidate mapping axioms or rewriting labels and definition content to facilitate matching, as well as generating mapping rationales or scoring plausibility or suggesting constraints to test mapping correctness. Now here you might leverage existing tools to confirm that, say, mappings don't introduce inconsistencies, and reasoners can derive cross-ontology inferences. You can also use them to construct shackle constraints or mapping quality control queries in Sparkle to pass to make sure that the ontology mappings are actually good, and then you can have this validated in a CI pipeline against the entire ontology stack, much like we have in the semantic pipeline itself. Ultimately, this final project really putting the icing on the cake here. It's a new era of ontology engineering. You are part of that new era. We are entering in this space, and we are carving up this space afresh. A lot of this stuff is new. It's not just about large language models, not just about machine learning, not just about ontologies, not just about symbolic methods. It's a principled integration of all of these technologies, and we are on the cutting edge of introducing that spear tip of all of them together. There's a lot of great research going on, don't get me wrong, in LLMs and ML, a lot of great research going on in ontology and applied ontology and ontology engineering. Nobody's doing this quite so intensely. This is where we're shining, guys, and this is where we're going to continue to shine. You are right here on the cusp. So I know it's a little Wild West, but hey, ain't that exciting? In any event, your final project, it's going to be a presentation. It's going to be to the class, and here you're going to include a live demonstration on the work you've done towards one of those two options. So again, let me repeat. Your final project will be a presentation. The last 2 days, the last 2 sessions of class are devoted to student projects, so that's when you'll be presenting them. You'll include a live demonstration on the work that you've done towards one of those two options, either the ontology mapping or the expansion of the semantic pipeline. And I'm gonna want you to talk for like a while. Depending on how many presenters we have, I mean, you may end up talking an hour. And we're gonna be peppering you with questions, don't worry. But you'll get up, you do your song and dance, just show us what you've done. We'll ask questions. We might ask you to add some data. I might have some data to play with, just throwing at you to see if you can handle it. It'll be fine. You'll be in a sterile environment. We just want to see what you've done. Just want to see how far we've pushed that needle forward. I believe in you. You can do it. Summary. LLMs, super impressive. Combination, ensemble of existing tools and strategies, trained against some massive amounts of data. Ontologies can be used to support them, or vice versa. And I like thinking of them best as used as middleware or glue between existing trustworthy tools. You will be aiming to leverage LLMs to expand your pipeline or generate and evaluate ontology mappings as a way. It's kind of a capstone on what we've learned at kind of a high level, just so we can see all the cool work you've been doing, your level of understanding, as well as your newfound mastery of these advancing technologies. Can't wait to see it.